Hello, welcome to Introduction to Composites. Today is the second day of the 9th week of this course, and yesterday we had discussed the variation of different elastic moduli and elastic constants of generally orthotropic lamina, a thin generally orthotropic lamina with respect to changes in the orientation angle of fibers, which is theta. Okay. Now, what we had discussed is how Ex, Ey, nu xy, mx, my, gxy, all these elastic constants vary with respect to changes in the orientation of fibers with respect to the loading direction. Now, what we will discuss are some more details on this, and specifically we will talk about balanced lamina and what that means in this context. So, these are the plots for Ex, Gxy, Gxy, nu xy, mx, my and so on and so forth for glass epoxy lamina, graphite epoxy lamina and boron epoxy lamina. Okay. Now, what you observe something very significantly is that in these cases, for all these situations, Ex is not equal to Ey, because Ex at theta is equal to here, for instance, for this thing, when theta equals 0, Ex is equal to El, and when theta equals 90 degrees, Ex is equal to Et, and Ex in general is not equal to Ey, and we can also say that nu xy is not equal to nu yx, and all this is happening because El is not equal to Et and nu Lt is not equal to nu Tl. Now, these so if I have to use a single lamina for some structural application, using these types of lamina may be disadvantageous in several cases, because if El is very large compared to Et, then we would also expect that the amount of load which it will bear in the L direction, in the longitudinal direction, will be much higher, and it will bear very little load in the T direction. But if it is just one layer we are relying on, then we would like that it should have similar load carrying capabilities and stiffness properties in both the directions. So, that can be accomplished if we have a balanced lamina. So, by balanced lamina means that its the value of its El and the value of Et is same, and also the Poisson ratio nu Lt and nu Tl, they are the same. Physically, this can be accomplished by having equal number of fibers in L as well as T direction. So, if you have same number of fibers in L and T direction, then El and Et will be same, and if that is the case, then we would also expect that for balanced lamina Ex and Ey will also be same. So, with this understanding, let us look at the plots for Ex, Mx, My and Gxy for a balanced lamina. So, here because it is a balanced lamina, El and Et are same, which is 21 GPa, GLT is 3.5 GPa and nu Lt is equal to, so this should be nu TL, nu Lt should be equal to nu TL, and that is 0.2. And if that is the case, then let us look at Ex and how does Ex change? It starts from 1 at 0 degrees and it keeps on going, and because this is my axis for Ex, it also ends up at the same value 1. Okay. So, Ex is symmetric, the curve for Ex is symmetric at around at the line theta equals minus 45 degrees. Ditto for Gxy, but Gxy was anyway symmetric even for not unbalanced laminates. But mu xy is also symmetric, and it increases to a maxima, but it again becomes 0.2. So, it is 0.2 at 90 degrees and it is 0.2 at 0 degrees, and then mx and my are also behaving. So, this is the relation for mx, this is the equation for my, and they also behave in a very symmetric nice way. So, these kinds of individual layers, laminas, they are balanced because of the fundamental reason that the transverse and the longitudinal modulus of the lamina are same, and also because the Poisson ratio LT and TL, they are the same. So, this is what I wanted to discuss about balanced lamina. Next, what we will discuss is some constraints which exist on some of these materials. So, before we do that, I would like to show you once again that for boron epoxy lamina, we have seen that the minima of Ex is not Et, right, is not Et for graphite epoxy and for glass epoxy. The minimum value of Ex was Et, but for boron epoxy, as per this plot, the minima is not Et, rather it is the minima exists when theta is somewhere between 50 and 60 degrees, it exists. So, what we are seeing is that for some lamina, Ex, so in this case, so e.g. boron epoxy, Ex can be less than Et, it can be less than Ct, and similarly for some other lamina, Ex can exceed El and Et. Okay. So, for some lamina, at least in case of boron epoxy, we have seen that Ex, so Ex min, I am sorry, I should have written min, the minimum value of can be less than that of Et and El, and we can also construct some other lamina, special lamina with specific properties such that their max can exceed El and Et. So, when does this happen? This is what we are interested in. So, the question is, first question, when does Ex min less than El and Et? And the answer to that has been given by an expert in composite, Jones, who is also the author of this R.M. Jones book on mechanics of composite material, and he has done mathematical calculations, and he says that if GLT exceeds EL divided by 2 times 1 plus nu LT, then Ex min is less than El and Et. Okay. So, this is the first question. So, if you find that in your composite system this condition is being satisfied, then you will have a situation that for certain value of theta, the value of Ex will be less than El as well as Et. Okay. The second question is, when does Ex max more than EL ET. And again Mr. Jones answers that it is more than EL and ET if GLT is less than, oh I am sorry, so this condition I specified incorrectly. If GLT is less than this, then this is less than this, and if GLT is more than EL divided by 2 times 1 plus nu LT, then Ex max it exceeds EL and ET. Okay. So, these are two important conditions which help us understand what could be the extreme value of Ex, extremum for Ex. And how do they get it? This based on mathematical analysis, not very complicated analysis, but we will not discuss this at least in this class. But if you are interested, you can refer to the paper by Jones and also his book, and you will find the details in there. So, this concludes our discussion for this particular topic. Now, what we will do is we will move on to the next topic, and that is about generalized Hooke's law. Generalized Hooke's law. So, what do we imply by this? So, our conventional Hooke's law, which we have talked about, it says that for isotropic materials, what is the Hooke's law? That if I have a bar and I apply a stress on it, and because of that it experiences a strain, then the Hooke's law says that stress by strain equals the Young's modulus, which is E. Okay. So, this is the Hooke's law for isotropic material, and an equivalent and similarly if it is in shear, then tau by gamma equals G, and then if the material is being compressed from all the sides, then pressure divided by volumetric strain is K, bulk modulus. And then, so this is for isotropic material. So, the question is, for anisotropic material, what we have discussed till so far is only for orthotropic material and anisotropic materials. Does a similar Hooke's law exist for a fully anisotropic material? That is what we are going to discuss. So, what we are going to discuss is generalized Hooke's law for anisotropic materials. So, before we look at it, let us define our axis system, and what we will also do is, so what we will do is that we will define our axis system, what are our 1, 2, 3 axes, and with respect to axis systems we will also have a consistent way of specifying stresses and strains. And using such a system, then we will then generate a generalized Hooke's law for anisotropic materials. Okay. So, this is the axis system which we use for stresses. So, you have a block of material and this material can be fully anisotropic. So, it may have different properties in different directions. It need not be orthotropic or isotropic, because those are just special cases of an anisotropic material, and we will use a Cartesian system of reference. So, this is our axis number 1, this is our axis number 2, this is our axis number 3. All the stresses on this plane can experience 3 types of stresses: sigma 21, sigma 22 and sigma 23. So, the first index sigma 2 corresponds to the direction which is normal to this plane. Okay. So, this is direction of normal, and the second index is the direction of force, direction of applied force. Okay. So, because stress is force divided by area. So, I am applying force in a particular direction and I am also applying it on a particular plane. So, the first index tells the direction of the plane and the second index tells the direction of the force, and as I had explained earlier, the stress is associated with 2 different directions, direction of normal of the surface and direction of applied force. So, it is a second order tensor, and in general I can specify it as sigma ij, where I represents the direction of the normal of the face on which it is acting and j represents the direction of the force which is applied on that particular surface. Okay. So, this is how I define stresses. So, we have sigma 21, sigma 22, sigma 23 on plane number 2, sigma 31, sigma 32, sigma 33 on plane number 3, and sigma 11, sigma 12 and sigma 13 on plane number 1, and likewise we have other stresses on the opposite faces also. So, these are my stresses: sigma 11, sigma 12, sigma 13, and this is the stress tensor, and it is represented by a 2 by 2 matrix, and in general I can also represent it as sigma ij. Okay. So, this is the stress tensor. Similarly, this is our strain tensor, epsilon ij. So, epsilon ij is epsilon 11. So, what are these? So, again, so before we go to strain tensor, these stresses are extensional stresses and all others, these are shear stresses, because the direction of the normal and the direction of the applied force are not aligned with each other. Similarly, on the strain tensor, these are shear strains and these are extensional strains. Okay. So, this is our overall framing of the problem, and what we have to develop is the relationship that how does sigma ij depend on, how does it depend on epsilon ij. So, this is the relation we will develop, and then we will call that relation the Hooke's law for generally anisotropic material, and then we will start working on that and we will finally come down to isotropic and much simpler materials. So, that is what we plan to do in our next class. So, please remember this terminology, and this is the terminology we will use starting from our next class. So, that is pretty much it for today, and I look forward to seeing all of you tomorrow. Thank you.